Last time we had a look at a new data type, the Boolean type, or just bool for short, which allows us to store a single bit of information, so just two possible states, and those values we can store are either true, which we actually write out as the word true, or it can be false. True and false. And the reason we call these keywords that way is probably because for the most part we only get Boolean values through analyzing statements we can make with special operations. And a statement can either be, or a logical statement at least, can be either true or it can be false. So I guess that's where it came from. And bool from Boolean logic, which is logic that operates on true and false. But those operations we can do that generate Boolean values are, for one, comparisons, which we can apply for integers, for example, or two integers, for example. We have an int a equals 1 and an int b, which is 2. We could now make b equal to a greater than, I should probably, let's recall this differently, maybe x and y. Otherwise I clash with a b. X greater than y. And now we have a statement, x is greater than y, and this statement can be either true or it can be false. And depending on that, b, our Boolean, is set to true or false. X is 1, y is 2, and 1 is not greater than 2, so b would now be false. Could switch this around to less than, and then the statement would be true. We had a look at other operations that generate Booleans that specifically work on Booleans, or at least the basic logic. And with that we had essentially two different groups of operations. Let's see, we had this one, and this one, and this one, and I think I showed you briefly this one. But they all had counterparts. Well, except for this last one. And the difference was that these operators on the left can be applied to not just Booleans, but also other data types, like integers, for example, again. And these are bitwise operations. So we have an AND on the top, an OR, a NOT, and an XOR. And OR, NOT, XOR. And the ones on the left would apply that logic to every single bit within a value. So if you have two integer numbers, which are composed of 32 individual bits, which are combined to generate that one number, these operators on the left would always be just applied to a specific position within that number. So only the very first bit of the first number and the very first bit of the second number generate the first bit of the third number. And the second bit of the first number and the second bit of the second number generate the second bit of the result number. The ones on the right here do not work on numbers, they are purely logical. So we have the bitwise operations and we have the logical operators. And the logical ones only work with the Boolean data type, and they generate Booleans. The general logic is still the same. Whether you use the left or the right version, it's still an AND, an OR, and a NOT. You can apply the left ones to Boolean types as well. The big difference was that these variations on the right, at least the ones with the double symbol, had an early escape. So if I have false and a true, the operators on the left, the bitwise ones, would just operate every bit internally which in case of a boolean is just 1 bit, but it still would compare both sides of the operation and generate a result. But if this was and, the logical one, it would look at the value on the left, it would see it's false and would not bother even looking at the one on the right. Because it knows it's an AND. If one side is false, the entire result is false, so this would ignore the right side and immediately determine that the result of this operation is also false. Which isn't that big of a deal now, but it will potentially become important in a couple of sessions. Generally, though, these are the ones you will use in your conditions, when you write statements. Not necessarily because of the shortcut, though that is nice, but not always. But more so to make the intent clear, that you intend to make a logical combination of different Boolean values instead of operating on numbers to generate new numbers, which is its own field of study, kind of. So the one on the left, that might cause confusion, and you might accidentally cause operations to work in a wrong way. The ones to the right are guaranteed to only respect Boolean values, so there's no mix-up with any integers you might want to tweak somehow. It makes the intent clearer, so that's more common. And something we used for demonstrating these Boolean operations, or basically the one thing we needed the Boolean type for and these different operations, was a new structure which lets us determine if a specific piece of code gets executed or ignored. I'm still just doing a recap so far, that's all stuff from the last episode, just the short version. So I have an int, let's use a again this time, 10, int b equals 5, and then we can have, let's say we want to have the absolute value of this, the absolute difference in here. Let's see, we have an int d for difference, which is a minus b, which will be 5. But I want to have the absolute difference, not just a difference. If a is greater than b, like right now, well, then everything's fine. Outcome will be 5, which is the difference. But if b is greater, if this was a 15, then we get a minus 5. And that's not what we want. We want still just 5. So we have to do something differently depending on the value of these two, or the relation between these two. And we did that using a code block that can be skipped or executed. And so we have a code block. And what this code block does can vary. Last time what we did was we simply inverted a number if it was negative, which we could do in here as well. We could invert d if it's negative, and that way guarantee that it's always a positive value. We could also just do the operation again, but flip the two sides, and that's what I'm going to do. I'm going to say d is b minus a instead of a minus b. And we close the block. And to make sure this block is only executed when a is less than 15, we have this little addendum on top, the if, which is just the keyword if, followed by normal brackets. And inside here we define a condition for this code block to be executed. And the condition was simply a statement that will result in a true or false. So just comparisons, for example, combined with logical operators. In our case, it's very simple. If a is less than b, we flip the two terms here, or not the terms. What's the name in case of subtractions? Can't remember, doesn't matter. And d will be a positive 5 this time. And that's basically where we stopped. And today we're gonna have first a closer look at this if block, because there are some things I haven't talked about yet. And to start with, let's say I don't want to do this subtraction twice. Because potentially I'm just doing a subtraction once, this if will be false, and then program is done. End. Okay, I can do this better. Come on. Ah, close enough. But if a is smaller than b, like with our example values 10 and 15 right now, then this operation will happen. We subtract b from a, and because this if will result in a true, we also execute a b minus a. We do two subtractions. We want to avoid that. So how can we do that? Well, first of all, let's make this a bit shorter. The trick I showed you last time. If there's only a single instruction on the block, we can simplify things by removing the brackets. The compiler will edit for us. It only works in that specific case where it's exactly a single instruction. An empty code block has to be written out fully, and everything with more than one instruction, so 2 instructions and more, or a code block and a code block. In any other case, you have to write those brackets. Only if it's exactly one instruction can we skip it. And let's skip this up here. We're not initializing that, we're just declaring that we have the variable. And then we do a different if down here, where a is greater than b. Like this. Okay. So in either case, if a is greater or b is greater, we'll just subtract based on the order that makes a positive number appear. We subtract the smaller number from the bigger number. And of course we have to encounter the third option, both values are equal. In that case, d is just 0. So now we have two if statements for two different cases. What if I don't want to have this comparison happen several times? Well, to begin with, we should probably clean things up a bit. Right now I have 3 different cases. A can be less than 15 than b, a can be exactly b, or a can be greater than b. Let's simplify that to just 2 cases. Either a is less than b, or it's greater than or equal to b. Like so. And in that case, we have only 2 options left. It simplifies our logic a bit. We don't have to worry about 2 different cases. We don't have to worry about the case where neither of them is true, because now one of them will be true. It's either less than, or it's greater than or equal to b. With this construct, what I could do to avoid making this comparison twice, I could introduce another variable. Only instead of an int, I should use appropriately the new type we learned about, bool. What do I call that? Let's call it flag. We've used the term before. This is flag, and we start out as, let's say, true. And with this flag, we now have the option to make a block, code block in here, and full one, because we have two instructions now, to set this flag to false when A is less than B. And we still say D is equal to B minus A. Subtract the smaller number from the bigger one. And then here we can just make an if without a condition and simply check flag. That is totally fine. A value is still a statement in of itself. The flag is either true or it's false. Now what cases do we have here? If it's true, that means this instruction was never set. It has the original value from the initialization up here. And the only way this flag value can be still true when we up down here is if this condition was also false. If this condition was true, we would go down into this line and set flag to false. Didn't happen, so it must remain true, so this must be false. So if flag is still true, that means A must not be less than B, which only leaves greater than B or equal to B. So this is totally fine. It's a very simple trick. We just start with the assumption that the flag is true. And if we show that A is less than B, we correct our mistake. Not true, set it to false. And we can use that knowledge now down here, because now we know that, yeah, flag is true or it's false, depending on was this condition true or false. And we can just reuse that directly without checking the same condition again. This construct, it's called that, is pretty common in programming. This, instead of having one code block that gets executed or not executed, we have two different code blocks and we want one of them to execute but not the other, but always exactly one of them. Very common. And so instead of always relying on this somewhat verbose construct, we can simplify it because the language includes a feature for that specifically. We don't have to worry about the Boolean. We don't have to store that ourselves. The system will keep track of that for us. And we do that by introducing a new keyword. So let's make this down here. Make this down better. So this is one code block. And this is another code block. And this up here was just a label to make sure that this code block is marked as conditioned. It's a conditional code block. It has a condition attached to it. If this condition does not evaluate to true, ignore this code. So this if is part of this code block. It's just giving it a label. It's giving additional info to this code block. And we can do the same to this code block down here with a different label. Else. ELSE. Let's try that again. Marginally better. Let's make this a bit smaller. Not only do we add a label to this block as well, we added this label with this block, which forms one unit, directly after this if block. You can imagine this is where this if stops. This up here is a completely valid if block. We have the if with a working condition, we have the curly brackets to denote the code block that follows, and we have an instruction inside. Perfectly valid. But then we add some... What the? Let's just do it this way, please. Touch is still not working correctly. I'm still not sure why. We continue down here with an else, and the compiler notices that. Even though this up here is complete and could work, the compiler knows that there's more down here. So it will continue the logic and will group this else with its own code block to this if. This is now one large segment of your code. The compiler knows all of this belongs together. And the meaning is specifically, if this condition is true, execute this code block. If this condition is not true, don't execute this code block. Same as before. This else down here now reacts to this code block being executed or not. If we finish this code block normally, if it was executed, we just skip over this. The else is completely ignored. But if the condition was false and we skipped over this first code block, we jump instead to the else and go into this code block. It's very simple. If condition is true, execute this upper code block. If condition is false, execute this lower code block. In both cases, it will execute some code. One of these blocks will get executed, no matter what. But only one will be executed. Not both. And it's purely a decision on whether this value is true or false. Two values, two code blocks. Now that we have this a bit more complex logic, we can bring it back to the more complex scenario from earlier, where we had 3 scenarios to deal with, not just 2. We've simplified logic a bit, but technically we have 3 variations: less than, greater than, and equal to. We mush the greater than or equal to together to make a subtraction here that might not be necessary. If both values are equal, why bother with making any math happen? Why waste those resources? Especially if maybe that's not just a subtraction, but instead some more complicated formula we have to calculate. So what do we do then? As I said, we have a Boolean value in the condition, which can only have 2 different states. There can only be a selection between 2 options, not more. So we can't change this if-else construct to have a 3rd option. That's not possible. Something like that doesn't exist in C#. If you know programming, you might disagree at this point, but that thing you're probably thinking about is not like an if. The fundamental principle by which it works is very different, and we'll get to that in due time. The if-else, however, is just binary option one or the other. To get the 3rd option in, we have to split one of these 2 options into 2 further ones internally. And we already made the choice up here is for less than, and the part down here is for greater than or equal. So let's split this up. And we extend this block a bit to contain another if, which is no problem. This is a code block that we start, and internally in that code block we can generate code blocks, no problem. And the if-else is also just a special type of code block, just one that might be ignored. And here we can check if A is greater than B. And if so, D is A minus B. And we can do another else. D equals 0. And we close this code block. as you notice. Same logic as with the if block itself. If there's only a single instruction, we are free to leave out the brackets. No problem. Yeah. Not only are we not bound to the brackets now, the curly ones, if there's only a single instruction, in general, we're also not bound to having new lines. So something I do here is move them onto different lines, but there's no problem in just putting them on one line. That's perfectly fine, that's valid code. You can do that if you want to. You can leave the else behind. This is the way I write code. I spread it out a bit further to the downwards. Takes up more space, but I find it vastly more readable. So now we have the option either a is less than b, in which case we calculate b minus a. And if that's not the case, if it's not less than b, it must be greater than or equal to. And so in the else block down here, we make another check. If a is greater than b, to differentiate that from the option that it's equal to b. So we have less than b, greater than b, and this can only be reached if it's equal to b, because there's only less than, greater than, or equal. There's no third option that can be. So this else is only if it's equal. This construct here is also quite common in programming. Not just this, it's actually going down further the rabbit hole, so to speak. We can nest other ifs in this up here, or this one in here, or this one in here. You can put if blocks inside other if blocks or else blocks, and inside other if blocks and else blocks you can put new ifs with potentially new elses. You can infinitely stack these up to make things as complex as you want. Which can be difficult to read sometimes. So something we do that's not part of the language itself, but the language allows it to do, is we rewrite this by just moving the bits around a bit. The first thing you need to understand, the reason we can just write the instruction below the if and below the else without any brackets is because the compiler knows something has to follow. This if or this else, those are labels to a code block. There is something that needs to follow this. And if I don't add the brackets, it will just assume, just take the next instruction you find and pretend that's inside brackets. Find the next logical unit within my code that follows the if. That is going to be either my code block or the content of my code block. So this if and this code block and this if and this instruction, they belong together. The compiler knows they form one unit, they're inseparable. You can't have them on their own. Same with the else. The else and its code block, or the else and this instruction, form one unit. You can't separate that. The compiler knows it. And because the else is extending an if, it also knows that this entire if code block, else code block is also one code unit. It's one group that belongs together. You can't... The undo doesn't work, the undo doesn't work. You can't have that in separate parts. I mean, okay, in theory you could have the if on its own, but then the else would be standing completely on its own, and that's not valid. So this if and this else must belong together. That's the only logical explanation. And because of that, we can actually cheat the system a bit and remove the brackets here as well. So it's not that we can remove the brackets if there's exactly one instruction. It's one instruction or one logical code unit. One clearly defined unit of code, which one instruction represents, or a code block represents, or a construct of two code blocks combined with an if and else also represents. As long as the compiler can guarantee that a certain group is created, that these lines belong together, as long as that is a guarantee, we don't need the brackets to make clear that these belong together. That's what the curly brackets would otherwise do. And because we can guarantee that these belong together, we don't need to specifically write that out, the computer is fine, or the compiler is fine without leaving it as is right now. But because it also doesn't really care about the extra byte space, the extra lines or indentation here, we can move this up here. A is greater than B. Put that up there. And this instruction, we still put that as indented, but we don't put that as twice indented for the indentation for the if and the else. We just do it once, like this one up here, minus B. And the else, also not indented, we put that in here. On the same line height, on the same depth as this else. And then the D equals 0. And I guess we can remove those brackets as well. This looks a bit weird now, but equals B minus A. Let's quickly move that up. And there we still have the same logic from earlier. We still have an if and an else. Just a binary choice between this block, or this one instruction, this code unit, or this entire code unit. Still a binary choice with this condition. And if this condition is false, so we do end up in this else part, so this entire block, our code will have a new if, which has a choice between this unit and this unit, which is both just a single instruction, based on this condition, which we have to evaluate first. So it's exactly the same logic as earlier. We didn't change anything about the way the program handles the code. We didn't change any rules. We just wrote it down in a different way, so now it looks like it's just a linear list going downwards. Check the first condition, check the next condition. If it's neither of those, do this. And we can extend this as much as we want. Could actually do an if A equals B. I'm not sure why we would do that, but we could do that. And have another else down here with something. This would not be the case of an if-else block with inside this else of this if-else block within this else of this if-else block. It's still a hierarchy where we go deeper and deeper into an if-else segment. But just by writing it out differently, it looks like it's just a linear list going downwards. Condition, 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 condition. So if you have several conditions to check, this is usually the way you write it out. It's not a feature of the language, it's just a way we decide to use the language features to write something in a more comprehensible way. Because the logic is essentially this. Check this condition, if it doesn't apply, check this condition. If it doesn't apply, check this condition. If it doesn't apply, go down here. That's the logic that will happen. And this way it's much clearer to see what's going on, instead of going down further to the right and have all these nested ifs. So we have the else if. Now, beware, in C#, this is how it works. There are other programming languages that have a dedicated else if, where this is not just a coincidence, it looks like that, but actually it's a nested part of that. The else if in those languages is an actual keyword, a specific meaning, to have it like this flat hierarchy of conditions, conditions, conditions. In C#, it's just coincidence. It's just the way we write it because it's convenient. Let's talk about some other types of branching. What we've done here so far was effectively what we did with conditional jumps in our assembly, where we could, based on some condition, which back then were much more primitive, skip certain parts of the code, skip forward, ignore some code. Right? This is what we do here as well. And if we combine this conditional jump with another normal jump, we also manage to create this if-else combination where we have two different types of code that executed based on another, based on one single condition. But the way we used jump in assembly was more than just skip code. We also had a way to jump back up to previous code, which resulted in the same code be executed again, and again, and again. Constantly repeat some code until some condition was satisfied or no longer satisfied, depending on what scenario we have. And the extended syntax, we used the term skip or skip block to make the conditional jumps that would move us forward, that would just skip code, clear. And we had a very similar looking counterpart to skip, which was the repeat, which lets us go back up top and repeat some code based on a condition. The same logic exists in C#, and unlike the if, there are actually a couple of different variations of this. See, this repetition has some more intricacies, just like the if has the additional if-else and some logic that comes with it. These repetitions also have their unique behaviors, and so we have different types of repetition, different ways to make the code work, depending on what circumstances we're operating with. And we'll get to see all of them at some point, but today we'll just focus on the simplest form, which is pretty much just like the repeat is a counterpart to skip, a counterpart to if. And let's try to write a code example that lets us make use of this repetition. Let's try to recreate a program we did in assembly. Remember, in our made-up computer, we didn't have a multiplication operation. So if we try to multiply a and b, we couldn't directly do that. In C# we can, of course. There's just a times b. We have multiplication here. But let's try to make the multiplication happen the same way we did with the assembly language, without any multiplication operation directly. And let's use the most primitive version we had. So we have a and b, and I want to have the product p, which we're just gonna start out with 0. And we can essentially skip the code if one of those two factors is 0, and in C# that condition is a bit more simple to construct. Just if A is 0 equals 0, or B is 0. Keep in mind, equals equals for comparisons, a single equals for assignment. Very important distinguishing factor. Compare, assign. You can make an accident where you forget to write two equals and by accident assign a value instead of comparing, which in this case the compiler would flag because the logic doesn't make sense anymore. But actually, let's demonstrate quickly. This would actually work. This is valid code, right? Nah, not quite, but it would almost work. Don't have to think to do much about it, but keep in mind, comparison is equals equals. Important. So if either of them is 0, we can ignore the entire multiplication and directly jump to the end. Which I'm gonna do this way. Of course, that means the code we write in here, the multiplication has to happen if it's not this. And the way we write that is we could either just invert the whole thing and put it in brackets. But I did demonstrate to you how we can invert a condition by hand to save some operation for the computer. First of all, we invert this from an OR to an AND. An AND would switch to an OR, and an OR switches to an AND. And these conditions also have to be inverted, which was easy with a less than or greater than. This requires now a different operator we haven't talked about. You know less than, greater than, and equals. You also know less than or equals, or greater than or equals. But there's a sixth operator I didn't talk about. And that's if we just want to see if it's less than or greater than, but not equals. And that operator is a combination of the logical not, which was the exclamation mark, and the comparison, which was two equals. It's just not equals. And this is how we compare that A is not 0 and B is not 0. So if both are not 0, then we will continue with the multiplication. And because of our algorithm, we can actually simplify it to if greater than, because our algorithm doesn't work with negative numbers. We can make it happen, but that requires some extra steps. So let's just pretend this only runs for positive integers. What our algorithm did, assuming both are at least 1, was repeatedly add a number. And we need to keep track of how often we made that addition, and we simply increased the output, the product, by one of the factors, and every time we did, we subtracted 1 from the other factor. And when that other factor hit 0, that meant we had all the additions done and the end product is reached. So we took P and added one of the factors. Let's use B now. And we subtracted 1 from the other then. A equals A minus 1. And we did that repeatedly until A is 0. So how do we repeat stuff? Well, the structure is very similar to the if, because it is fundamentally the same thing. If you think about the if block being a conditional jump operation that goes down, so if something is false, we just go down directly. But if it's true, we execute. So it's just a matter of, do we skip this entire block or not, based on a condition. And let's assume that all we did is add a jump instruction right here, at this close bracket. Right after this code executes, the last thing we do is jump back up here, where we made the conditional jump that would lead us down here. That is basically exactly what we did in our assembly program. And we can make that happen in C# directly as well, by just switching out the keyword. Instead of an if, we use while. And then we still have the normal brackets with a condition, while a could say not equals 0, but I prefer to do greater than 0, because we have the assumption already that a is greater than 0. It only works if it is, and we go downwards to 0. For one, it's one less symbol, it's easier to read, but there's another reason, and I'll try to remember to mention that later. Let's ignore that for now because it's not too important. It's my preference only. And with this, well, honestly, we're done. This is it. That's our program. Let's quickly get rid of this. Just like with the if, we have a code block that has the special label that this time refers to not just skip this code block if the condition is false, also repeat the code block as long as the condition is true. And that works exactly like I mentioned with the jump instruction in assembly. We first evaluate the condition, and if that condition is true, we execute this code block. If the condition is false, we jump behind the code block. The only difference is that with the while, once we exit this code block, once we hit this curly bracket and we're done with the code block, we leave the scope, we first go back up here. We don't continue with the code down here. We go back up to the very top and start again with the while. As if we never checked this, as if we reached this point for the very first time. And we check the condition, we evaluate the condition fresh, and check if it's true or not. And if it's true, we execute the code, and then reach this part down here and close the bracket. And then we go back up to the while. And as if we're looking at it for the very first time, we try to evaluate the condition. If it's true, we execute the code, until at some point this condition evaluates to false, at which point we jump down here. So we have this thing down here which would go back up to the top, and this thing which would either go in here or down here. So we go down here, there, back up to the top, or we go directly down here and continue our normal code. That's a while. It's pretty simple structure. Just like the if, with the additional benefit of it will try to make the whole if happen again. In fact, it's so much so like an if that we can immediately see the duplication. We have an a greater than 0 here and an a greater than 0 down here. Why bother? Leave that out and just make it b greater than 0. And still writing the side. Oh, that's better. If b is greater than 0, then we enter the scope block, and if it's less than 0 or equal to 0, we go down here. And if we enter this scope block, we see a while, so we evaluate this condition. Is a greater than 0? If not, then we leave this scope block, and then this scope block, and we're done. Product is 0, which is correct. But if b was greater than 0 and a was greater than 0, we will first add b to p, and then subtract 1 from a, and then we repeat this condition only. Is a still greater than 0? We didn't change b, so we didn't need to look at b. We don't care about the value of b anymore. We only need to change, or we only change a, so we only need to check a again. Add b to p, subtract 1 from a, check a again. Repeat until at some point we reach a being equal to 0, and then our program is done. The reason I chose a greater than 0 is, well, in this case it's not really that beneficial. It's just paranoia at this point. But if it's a larger complex program, you will want to make sure that this condition will reach false at some point. You want to make sure that this is not eternally gonna repeat, because that would mean your program is freezing. You're waiting for any response, it's just stuck and it's never gonna continue working its normal job. So always make sure that this condition will end appropriately. The reason I chose greater than 0 is because often with larger code it can happen that either because of something unexpected happening or because you had an oversight in the code doing its thing, you might skip a single value. So instead of just subtracting 1, we might accidentally subtract 2 at some point, and then we might skip 0 altogether. And that's not exactly a problem for integer values for a simple code like this, but it's a habit that I've picked up that I always follow basically for everything. If a goes to the negative values, I abort this loop. It's technically not a valid code anymore, so I should probably have some error handling, which is a topic for far, far later. But at least I can be sure that the loop will end and the program doesn't freeze. So just personal preference. A not equals 0 would be perfectly fine. I prefer greater than 0, does the same job, but handles some special cases where the program otherwise would break completely. Also in this case, we can exclude negative values as the input, which is a nice bonus. So this is the while loop. And something important about the while loop that I'm going to demonstrate with a simpler program. Just we have just an int a. Actually, let's make this semicolon a bit better. While brackets a greater than 0, a equals a minus 1. So doesn't really do anything useful, but it's valid code. Why did I show you this? Let's have a look at what happens if we introduce our table again. Say we type name value. You know the drill. Actually, let's not bother with that. So, introduce the program. We start with int a equals 10. So, first instruction, int a equals 10. We have two operations, declaration, assignment. We have to do the declaration first. We check for a variable named a in the table. It doesn't exist, so it's free to use. So we declare an integer value a with nothing. Then we perform the assignment operation, we set a to 10. And instruction done. Now comes the while. Just like the if, not itself an instruction, but just structure. What we actually have to do is comparison. Evaluate the statement a greater than 0, like an instruction. Just perform operations. That's what an instruction is in the end. A greater than 0, we look up a, which is 10, and 10 greater than 0 is true. So the value inside the condition here, the condition field, is true, so we do execute the code block that follows. And if you remember, code blocks, scope, these brackets mean we start a new table. We still keep the old table around, but we also have a new table. Now the instruction, set the code block, a equals a minus 1. We have the assignment and we have the subtraction. Subtraction has priority over assignment, operator precedence. So we have first a equals a minus 1. We look up a, find it not in this table, but in this table above, to a value of 10. 10 minus 1, so a equals 9. Subtraction is done. Assignment. Assign 9 to a. Don't find a here, but up there, change it to 9. Instruction is done. And with that, this code block ends, so we now remove this table. And because it's a while, we jump back to the top and evaluate the while again, which means we evaluate a greater than 0 again, which will still be true, and we go into the code block and evaluate that. But the important part is that every time we stop the content of this loop, after evaluating the condition, we create a new table, we do our stuff, and then we remove the table before starting again. So if I have a new variable in here, and b equals a, then a equals a minus 1. What happens now? This is more of a test, this is not something new. You should be able to decipher what's happening here. We start with a loop, a is greater than 0, let's skip that part, it's true. We start a new table, type, name, value, whatever, and then we have the int b equals a. Declaration, assignment, declaration as priority. We check for the name b, doesn't exist here, we're free to use it. So we introduce a new type b, which we add to the new table, to the newest table we have, the lowest one. Initially no value, then we have the assignment of a to b. We look up a, can find it up here with a value of 10, we assign a value of 10. This one is done. Then we do the whole operation of a minus 1 and assign it to a. We've done that just a few seconds ago. So we're gonna set the value at a to 9. And then we leave the code block. So we remove this entire table. And now we start the whole thing again with a while. We check the condition. A is greater than 0. So we enter the code block and make a new table. And then we declare a new variable b and set it to a in this new table. When we declare it, it will start out as nothing, undefined. We assignment a is 9. Then we increase or decrease a by 1. and we leave the scope of the variable, the while, and we delete the table. It's not deleting the table. Now it's deleting the table. So just like with normal code blocks, the variables we create inside this code block remain in the code block. And when we repeat this whole thing, it is as if we left the code block first and then entered a new code block. So this loop, even though it's the same code block, will treat this as a completely new code block and it will create a new variable b. It's as if we have parallel versions of this code block. So if we just had an if here, that was just copied below. We tried that again and again. Nope, don't want to see that. So inside a loop, every time... Oh yeah, but I didn't mention the name. So this while... Not while, while. While a greater than 0. This construct is called a loop. That's the general term. Loops are blocks of code that repeat. And there are different kinds of loops in C#. This is a while loop. The simplest one of all. It's just the term while, and the condition, and the code block. As simple as it can get. And the logic is pretty much that of the if, so if you understand an if, you understand the while. There is no else though. Just to mention, there is no else you can attach. Also not on a different name, doesn't exist. So with an if, you have a binary choice between two pieces of code. With a while, you have just the binary choice of the same code or no code. But the important bit is, you don't keep the variable b around. You declare it once, it only exists until we reach this point, and once we repeat the whole loop, b is a completely new variable, as if it never existed in the first place. That is important to understand. Will be very important to understand for some of the other types of loops later on. And since we're here, maybe introduce some additional operators. As far as the structures go for if else, else if, and while, that's it for today. There's nothing more to that. I'm just gonna talk about a few operators now, because they're useful, save you some time. A equals a minus 1 is a very common type of operation. Just in general, this I'm changing a specific variable that exists by doing some operation on it. Could also do minus 2, same. Or plus 2, or times 2, or whatever. Those are very, very common operations. You take a variable, you change the variable, but you save the result in the same variable still. And to save yourself some trouble, within C# you can make a shortcut for that. So I can write a equals a plus 1, but I can also do something slightly weird. We do the operation we want to do after the name, and then follow it up by the assignment, and then the value. So put that up here, put that up here, and we skip that. So a equals a times 2 would be a times equals 2. For example. So for, at least for the math operations and some of the binary Boolean operations, bitwise Boolean operations, you can just write it out as the variable you want to change, the operation you want to perform on the variable as the first argument, and then the assignment operator followed by the value that is used as the second value you want to combine. So this is just a times 2, but assigned directly to a. You might get a bit confused sometimes because of structures like not. So I could have a Boolean b equals true, right? And I can set b to not b, the logical not, which will just invert this. So b is now going to be false. Not b is false, and we assign that to b, so b is now false. That's an example where you can't do that because, well, for one, there's no need to. It's still the same amount of symbols, and the not equals is reserved for comparison. So that's an example where the logic doesn't hold up. But usually if it's involving two values, if it's an operation that has two values, one on the left, one on the right, you can usually write that as a simplified form where you skip the variable name a second time if it's changing the same value that is also part of the operation. You can also do that for variables, not just constants. So, and you can even do it for all operations. You can do something like and b equals 2, like that. So you could do a plus equals b times 5. Totally valid. This would be a equals a plus b times 5. I mean, the brackets technically not necessary. Probably better if we switch this around. So times equal b plus 5, this would be times. So that's important. These brackets are technically there. So this will be calculated first, and that's multiplied by a to save it to a. These are equivalent. You can see it's just saving a bit of extra space. Plus, if you're reading this code, you know immediately, okay, we're using a and change a, and we don't have a third variable involved. We have just a and b, and that's it. Can make it a bit easier to read. It's a bit quicker to write. Can do that for most operations. And specifically this operation and this one as well. These are so common that not only can you do these, there's even a third way we can do that, specifically for the +1 or -1. Explicitly 1. Increment by 1, decrement by 1. +1, -1. Add, subtract, 1. For specifically those, we can write this or this, and that. We can use the ++ operation or the --. And you can do that as a ++, you write the two pluses behind, or you write them in front. And all of these lines are completely valid code. And trust me, as weird as it looks right now, you'll get used to it so fast. You see it in code all the time. It's very, very common thing. You ignore that ++. It pops into your side and you immediately know what's going on. You will get used to it very fast. It's very convenient. Plus, again, it can only exist this very specific case of +1, -1, So if you see a plus plus or minus minus, you don't have to think about any other variables that might be involved or values you might need reference. You know exactly, okay, increment, decrement, done. We change the value and we immediately know how it's changed. By what value. And now comes the funniest part. Why do we have two variations? Both of them are valid. And both of these do exactly the same. In this context. Because there's nothing else happening here. So just to fill up some time, I'm demonstrating this part now. Let's say b equals I'm gonna save the simplified version for now. B plus 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 a. And b equals b plus a plus plus. Looks very weird, doesn't it? It looks silly. And it is. But it works. This is both valid code, and both instructions do similar things. But the outcome is different. So let's try to execute these two lines of code. Might treat them as two separate codes, we're not gonna mix them in one program. Let's start with our code up there. Okay, so let's assume these two instructions are done. This is gonna be the state of our table. And now comes the b equals b plus 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 a. This is a bit of an issue right now, because this could mean two things. Is it b plus 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 a? Or is it b plus 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 a? Should probably make that clear first. I'm specifically talking about the plus plus a. So b plus plus a. When you write that out, usually you also would have some space here. Right, so the brackets are enough, I guess. So how this works now is we still break down the operations. We have the assignment here, we have an addition here, and we have the increment operator here. The increment has priority over the addition, which has priority over the assignment. So we start with this, plus plus a. What is going on? Weird things are happening. Let's just leave it like this. It works. So plus plus a is itself a full instruction that's basically a shortcut for a equals a plus 1. So increment operator, we go to our table, find a, and increment the value by 1. To 11. And now something specific happens. This operator is not only an instruction in of itself that increments the value, it will also result in a value. So in that case, it's both a equals a plus 1, but you can also treat it as a plus 1. And in fact, this and this has the same result. So the secret I've kept from you so far, b equals 1, is not just an instruction of itself. The assignment operator is a legit operator. Assignment operation itself returns a value. Just like b plus 1 returns a value, it is the result of b plus 1. The assignment operator also is a value. It is resulting in the value that is assigned to this. So I can't just assign 1 to b and then add 1 to that and assign that to a, for example. Assigning a value will result in the entire expression being equivalent to that assigned value. So a equals a plus 1 will first add 1 to a. So in that case that was 11 originally. And then the assignment happens. And we assign 11 to the value in a, the table. But then this whole thing itself results in an 11. It is an operation with an outcome, with a result. So when this happens in here, what we end up with is b plus 11, the assigned value. Now we can continue. We have the addition next. B equals b, look up to plus 11, which is then b equals 19. We perform the operation, and then lastly the assignment again. Can skip that part for now. B equals 19. We set it to 19. 19. Why did I think 19? 13. Can't calculate anymore. Assign it to 13, and this will result in a 13 itself. It's just that we don't do anything with that result because there's nothing else left, no operation after the assignment. So the 13 gets dropped. We ignore that. But it is still processed and it's still the outcome of the entire instruction. So how did things work with the other version? Let's reset. We are after these two instructions. Now let's look at this one. B equals b plus a plus plus. Now this time it's a bit more clear. This plus plus can only belong to the a. And the increment operator, decrement as well, has precedence over the normal math operations. So we're first gonna hit the increment again. So essentially again, a equals a plus 1. So we take a, it's 10, so a equals 10 plus 1, increment to 11, a equals 11, and we make the assignment happen. A is now 11. Only something weird happens if you do the plus plus or the minus minus on the right side of the variable, after the variable. When the increment happens, the outcome will be the value of a. But with the plus plus in front of the a, or the variable, on the left side, as we did earlier, it is the value we just assigned, the new value. That was 11. If we put it on the right side, the outcome is the value before the increment. So that was a 10. So now we end up with b plus 10. We look up b, it's 2, so that's 12. And we assign 12 to b. So a, in both cases, will be set to 11. The increment happens. A is the same as before, but b will have a different value. So the increment on decrement operators can either be written as increment on the left, followed up by the variable, or start with the variable on the left with the increment or decrement on the right. If it's on the left, we first increment and then read the value for the other operations surrounding it. And if it's the variable first, we first read the current value of the variable and then increment it. And the current value is what's used for the operation. That's how you can think of it. Maybe it's a helpful guide. Gets even better if we combine it. Let's ignore this part for now. So we could have a plus 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 a. Let's say b equals. This is one of the more extreme examples. We have now assignment operator, increment operator here, addition, increment operator over there. The increment operators have equal priority, so between the two of them we start with the left and then go to the right. Then followed up by the addition, and lastly do the assignment. First operation, a++, so we increment a to 11, but the variable came for the increment. We have a++. So the value that this operation results in is the value of a before the increment. So this is 10 plus a. And then we have this increment operation where we will increment first and then take the variable value. So we do 12 in there. And that will also be written down here. And then we do the operation, which is just an addition, 22, and assign that. B is now 22, and that if itself returns a 22 as a result of the operation, which is not used, so it's as if we didn't need that step. That's the weird world of increment operators. And that's why you can write this or this. Both will just increment a, and in this specific case, if you write it on its own, the difference between the two doesn't matter. Technically, this results in a different result value than this down here, but because it's never used, you only see the differences it makes in the table, which is the same. A is changed the same way for both, it's just how we use it in context that makes the difference. Might need some getting used to it. Just keep in mind there's a difference between variable first or increment first. Read the variable, then increment, or increment, then read the variable. The order matters. If you write that as a single instruction, like we did here, it doesn't matter. They're exactly equal. Oh, maybe heads up. If you're a performance freaks and like to optimize things ahead of time, technically there's a minor difference in terms of performance between these two in C#, but if you write that out as just an instruction, it's perfectly identical, though it doesn't make a difference. And even if you use it in a context so that the difference does matter, the performance difference is negligible. In terms of processing time, it's the same, and it's only technically using a bit more memory, as in just one value on the IL stack. It's nothing. It's just, seriously, just ignore that. So other languages might have actual performance differences. Depends on the language. In C#, it doesn't matter. Yeah, and that's where we stop. We've seen alternative branches in if with the else continuation to allow for two competing code blocks, of which exactly one will get executed, guaranteed. We've seen how you can combine ifs inside another if, and then just write that out slightly differently to make it appear as if we had an if, else if, else if, else if, like a whole range of alternative code branches based on continuously evaluated conditions. And we had a look at our very first loop, the very basic while loop. Plus some interesting stuff about things to keep an eye out for because of scope, code blocks close and delete their data, and some fun stuff you can do with simple operations that have shortcuts in the language. I think that's enough for today. Have a lovely Sunday. Till next time.